Right, we're going to jump into some examples. We know our linearization formula right there. L of x equals f of a plus f prime of a times the quantity x minus a. Again, we're calling it this new name, but it's really just the equation of the tangent line through a certain point. X is the value we're trying to approximate, and a is something easy that's close to x. Okay, let's check out a couple of these. We're going to use linearization to approximate 2 raised to the 4.986 and the cosine of 1.7. Let me switch it over here. Example, use a linearization to approximate. Okay. In part A, 2 raised to the 4.986. All right, so in the end, right, we want this. Copy our formula over again. And we got to figure out, all right, well, what will the function be, f of x? Then what is the x value and what is the a? What should we take as our function? Think 2 raised to the 4.986. We're going to take our function to be 2 to the x. Okay. Where, of course, x will equal the 4.986. This gets plugged in at the very end. What should we take a to equal? Well, a needs to be something that's easy to calculate, that's close to our x value. I think here, this would be a lot more interesting if we were all in class together. What do you guys think? What should we pick for a? Well, I would recommend picking a whole number. Let's just take 5, because we can easily take 2 to the 5th. That's not difficult to find. And it's pretty close to x, really close to x. Okay, so what we'll need to do is find f of 5 and f prime 5. Let me find f of 5 just while we're here before we do a derivative. So plugging that in, 2 to the 5th is 32. All right, and now we'll find f prime 5. So let's see, to take a derivative, f prime, derivative of 2 to the x, maybe you remember that's 2 to the x, natural log of 2. And we'll find the value at 5. So that's going to be 2 to the 5th again, times the natural log of 2, 32 natural log of 2. Okay, looking good. I know f of 5, I know f prime 5. All right, so here L of x, our linearization, is 32 plus 32 natural log of 2 times x minus 5. So this equation right here, the equation of the tangent lines, all it is, going through our point there at 5. This is like, we're like flattening out the actual curve just for values close to 5. All right, so to finish this off, all we're going to do is plug in our x value, L of 4.986. 32 plus 32 natural log of 2 times 4.986 minus 5. At this point, we're going to recognize I could do that, by hand if I wanted. The natural log 2 makes it a little tricky. That's not we're just going to grab our calculators here. All right, 32 plus 32 natural log of 2 times the quantity 4.986 minus 5. Now, if you're thinking, hey, like really natural log of 2, this value actually would have been well known even before like calculators and stuff, technology was around. People in the old days, they had these huge tables, these huge books with values of this stuff. So they could easily look that up. You know, something like natural log of 2, no problem. They can get a really accurate value of that, put it in, do it all by hand. Okay, but that's not the way we work today. So I'm just going to put it in a calculator. And here's what I got. We're going to round this to 4 places, 31.6895. If I go to 4 place values, there's our answer. We have approximated 2 raised to the 4.986. Pretty good. Now, this is like going beyond, but just for fun, I mean, how can you resist? You got to put in 2 raised to the 4.986 into a calculator and just see how accurate that was. And, you know, that helps you like check your answer too, because if you're way off, that's bad. 2 raised to the 4.986, doing that right now. And check this out, 31.6909717 ... Just how accurate were we? Well, we got the 31.6 perfect, and then 895 or 89 became a 9. That's ridiculous how close that is. So let's see. We were, so 90 compared to 89, we were off by only one 10,000, tenths, hundredths, thousandths, one 1,000th off. Unbelievable. Pretty sweet. Okay. Plenty accurate enough for any purpose somebody might have if they're building something, measuring some angles or whatever. Okay, number 2. We're going to check out the cosine of 1.7. Again, I'm going to write out our formula just so we know like what our goal is here. And we can put together all the pieces. Okay. What should we take as our function? All right, you probably caught on. All right, it's the cosine of x, probably a good idea. And we'll make x 1.7. We'll plug that in the end. Now, this is kind of interesting. What should we pick for a? Right? Sometimes a is really obvious. Sometimes it's a little bit less obvious. A value that's close to x that we could easily plug into this and arrive at an answer with, you know, without a calculator if that's what it came to. We can even easily get the value without a calculator if that's what we need. When it comes to trig, right, you're like, the things that would be good to plug in are like, you know, different ratios of pi over 2, pi over 3, that sort of thing, pi over 6. So let's see, 1.7. What ratio involving pi is the closest to 1.7? And it turns out it's pi over 2. Pi over 2, you know, if you were to guess and check, pi over 2 is about 1.570, kind of straight on me there. 079, right? I put it in my calculator just now. I don't remember that. All right, so this is as close as we can get to 1.7 and have a nice value, nice, clean, easy value for the cosine. All right, so that'll work pretty well. So first thing, all right, hey, let's get f of a. Let's get f of pi over 2. Cos pi over 2, what's it gonna be? What's it gonna be? My calculator was in degrees. I knew it already, but I just wanted to check. All right, so cosine pi over 2 is 0. It passes through 0. All right, we'll also need to know f prime of x, so we can get the derivative there. Let's see, derivative cos x, negative sine x. And we'll need to know f prime pi over 2. Well, negative sine pi over 2 is going to be -1. Sine pi over 2 is 1. Now this is interesting. All right, so we got our values 0. Okay, well, it is what it is, and then -1. So L of x will be our f of pi over 2, 0. Our derivative value was -1. All right, so 0 minus 1 times x minus pi over 2. Now this we could simplify if we wanted. Let's call it negative parentheses x minus pi over 2. We could even distribute the negative if we really wanted to, because it's so simple. Generally, we're not going to simplify these things at all. So I would say just get rid of the 0, if anything. Okay, looking good. Only one more step. There's our linearization of cosine 1.7 when we're close to pi over 2. Last thing, plug in our x value. So we'll take L of 1.7, negative 1.7 minus pi over 2. And at this point, we're going to pick up our calculators. Boom. All right. 4 decimal places. Negative 0.1292. There's our answer. All right. Oh, okay. Oh, sounds good. Of course, we want to check what is it if we put it directly into a calculator. Make sure you're in radians. The cosine of 1.7, negative 0.12884494, and so on. Okay, that's pretty good. Again, like all of these, I don't know if this is a coincidence, but like all of these are in the thousands. Here, well, see, 88 compared to 92, we're only off by 4 10,000ths. Unbelievable. That's really fun. Can you believe just how accurate that is? I mean, it didn't take us all that much work, right? I mean, I was like spacing it out. I mean, it took me a page, kind of spaced out, but it's not like anything I was doing was all that wild, really, compared to other things we've done in this course for sure. And we got the value of that within 4 10,000ths. Crazy. Okay. Before we stop this video, let me go back to our lecture. Okay, so we completed both of those. Here's a good follow-up question that, maybe we haven't really been thinking about so much, but like would be natural to someone in the old days if they were really using these. Can we know whether the approximation we just found is larger or smaller than the actual value? Okay, so we know when we get an approximation, we're pretty close. We know we don't have it perfectly, right? We get it, we accept that. But wouldn't it be nice to know if the value we just found was actually a little bit larger than the real value, or a little bit smaller than the real value? Right? Is that something that we can know in our approximation if we were a little too big or a little too small compared to the actual value? Yes, we can totally know this. We're going to look, it comes down to the graph. If we can look to see whether the tangent line that we used falls above or below the curve at the value that's being approximated. Okay, let me jump back over here to my drawing. Let's go back to the linearization of our part A. So 2.4, 2 raised to the 4.986. Okay. If you graph that, and this will just be a sketch, 2 raised to the 4.986. 2 to the x, right? It's exponential. It's going up really, really fast. So it's going, it's shooting up like this. F of x equals 2 to the x. right? And so we thought, okay, where did we take our tangent line? We took our tangent line at 5. So let's say 5 is here. This was at 32, right? So our tangent line did this here. Well, when we did our approximation, it was for 4.986. That's a little bit to the left. And I don't, my drawing's not, oh man, I really like drew it right on top. But let's say this is 4.986. Well, they're like right on top of each other, but we can see that the tangent line falls below the actual curve. So we found the point on the tangent line, it's below the curve. So that tells us our approximation is a little bit smaller than the actual value. And that is in fact what happened. Our approximation is just a tiny bit smaller than the actual value, right? We had 0.68, it's actually 0.69, a little bit smaller. Okay, let's check it out for the cosine. Cosine 1.7, okay, so this drawing, now cosine, let's see, 1, -1. Okay, so the cosine starts up here, and let's say this is at pi, something like that. Here's 2 pi, okay. So it drops down like this. Okay, we get it, something like that. So where did we draw our tangent line? At pi over 2, we drew our tangent line right here. So we think about that tangent line, and again, not the best, but okay, we get it. Something like that. The x value was at 1.7. Pi over 2 was at 1.57, so 1.7 is just a little bit to the right, which tells us that our approximation, again, our tangent line is below the actual value on the curve. So our approximation was a little bit too low again, because our tangent line was beneath. Is that really what happened? Yes, they're negative values. We're a little bit more negative in our approximation than the actual. We're at negative 0.129, and it's actually negative 0.1288. So we're a little bit below the actual. And then we kind of talked about at the beginning when it was square root of 4.37, right? F of x equals square root x. This one turned out to be a little bit higher, right? So we had it at 4. This time the tangent line was above. So when we found it at 4.37, there our tangent line is a little bit higher than the actual value. And so our approximation was just slightly larger, slightly bigger than the actual square root 4.37. Okay, so we can, that's pretty good. We can learn a lot, get approximations, even though if they're a little bit too big or a little bit too small. Let's stop this video here. See you in the next one.